Welcome to The Explainer. Today, we're diving into a topic that's, quite frankly, terrifying, but absolutely fascinating from a scientific standpoint. We're talking about the actual physics behind nuclear weapons. You know, we constantly hear about the geopolitical fallout or the massive price tags, but we rarely get a real step-by-step breakdown of exactly why they are so devastatingly powerful. So we're going to demystify the mechanics inside these weapons and break down the complex science of mass destruction into pieces that actually make perfect sense.
Okay, let's dive into this. Here's our roadmap for today. First, we'll look inside the atomic bomb. Second, the hydrogen bomb upgrade. Third, measuring nuclear devastation. Fourth, the invisible threat, radiation. And finally, number 5, the global nuclear arsenal.
Let's kick things off with Section 1, Inside the Atomic Bomb.
To really understand a weapon of mass destruction, we've got to zoom way down to the microscopic level. An atomic bomb is basically built to trigger fission. And what that means is it's a chain reaction of splitting heavy nuclei to release just an immense amount of energy. If you look at one of these things from the outside, it usually just looks like a big, rounded torpedo. But the real secret is what's happening on the inside. You see, you can't use just any material for this. You need incredibly heavy, highly unstable elements. Usually, we're talking about uranium-235. But raw uranium doesn't just spontaneously explode. To get that maximum energy out of it, the uranium has to be highly enriched, meaning that the 235 isotope makes up at least 80% of the material. Now, if that incredibly difficult enrichment process fails, scientists do have a fallback plan. Plutonium-239, which is actually an artificial element created specifically for this exact purpose. The ultimate goal of using these specific fuels is to reach what physicists call critical mass. Think of it as the exact amount of concentrated material you need to trigger a totally self-sustaining runaway nuclear decay reaction.
But here is the truly terrifying reality. To get a massive city-leveling blast, just reaching one critical mass, that's not enough. You actually need 4 to 5 critical masses reacting all at once. So how on earth you achieve that? Well, weapon designers use a brilliant yet highly destructive method called implosion. Imagine the core of the bomb is a small ball containing our uranium or plutonium. Step 1. External explosives, packed tightly all around the outside of this core, are detonated simultaneously. Step 2. This creates a massive shockwave, but it doesn't blow outward. Instead, it shrinks and completely crushes the space inside the bomb, right toward the center. Step 3. This incredible inward pressure violently spikes the density of the radioactive fuel, instantly forcing it to reach those 4 to 5 critical masses. And finally, Step 4. The catastrophic nuclear explosion itself. It's basically a perfectly timed inward squeeze that releases an absolute outward nightmare. Moving right along to Section 2. The hydrogen bomb upgrade.
Now, what's really interesting about this slide is how it breaks down the evolution of these weapons. Once atomic fission was mastered, scientists immediately started looking for a way to magnify that power, and that led to 2 completely distinct eras of nuclear weapons. Fission, which we literally just covered, generates power by forcing heavy, unstable nuclei to split apart. Thermonuclear fusion, however, is the exact opposite physical process. Instead of splitting heavy elements, fusion works by violently combining or fusing incredibly light elements together. It's actually the exact same process that powers the sun and the stars, just brought down here to Earth.
So a hydrogen bomb uses hydrogen isotopes called deuterium and tritium, but the main active substance is a compound called lithium hydride. But here is the mind-blowing part about all of this. Lithium hydride won't just explode on its own. You could hit it with a hammer and nothing happens. It actually requires an environment of unimaginable heat and pressure to even begin fusing. So how in the world do weapon designers spark that reaction? They use what's essentially a terrifying Russian doll technique. To detonate a hydrogen bomb, they literally place an entire, fully functioning atomic fission bomb inside the casing. It acts as nothing more than a detonator. You need an entire atomic blast just to create the initial spark that triggers the lithium hydride to fuse. And because of how this fusion process works, theoretically there's absolutely no limit to a hydrogen bomb's power. You can literally just keep adding more fuel to it.
All right, Section 3. Measuring nuclear devastation.
With weapons that are this ridiculously powerful, how do scientists actually calculate and compare the physical force of these reactions once they're finally unleashed? Well, to understand the scale, we really need a grounded universal baseline. Enter the TNT equivalent. This is a metric that simply calculates how many tons of conventional TNT explosives you would have to pile up and detonate all at once to equal the energy released by just one nuclear blast.
Because the numbers get astronomically high so fast, we measure atomic weapons in kilotons, which means thousands of tons of TNT, and hydrogen fusion weapons in megatons, which means millions of tons of TNT. And this brilliantly illustrates the terrifying shift in power. The transition from atomic to hydrogen weapons literally changed the world forever. The two atomic bombs dropped in 1945, Little Boy on Hiroshima and Fat Man on Nagasaki, had yields of roughly 13 to 18 kilotons and 21 kilotons, respectively. The devastation they caused was total and absolutely horrific. But I want you to compare that to the Tsar Bomba. That was a thermonuclear hydrogen bomb detonated in a test. Its yield, 58,600 kilotons. That is 58.6 megatons. It represents a theoretically limitless leap in technology. To put that into perspective, to match the sheer force of the Tsar Bomba, you would literally have to detonate over 3,000 Hiroshima bombs at the exact same time. It's almost hard to wrap your head around.
Let's move to Section 4, the invisible threat, radiation. The immediate shockwave and blinding light of a nuclear blast cause immense physical destruction, obviously, but it's the silent, invisible aftermath that makes these weapons uniquely horrific. If someone survives the initial blast, the surrounding area becomes heavily contaminated by ionizing radiation. Basically, there are three main types of radiation released. First up is alpha radiation. Now, it's dangerous on direct contact, but surprisingly, your basic clothing or even unexposed skin is actually enough to protect you from major harm. Next is beta radiation. Okay, this one is far more serious. It's capable of causing damage from tens of meters away. You have to actively protect your mucous membranes, and exposure leads to severe radiation burns and cataracts. And finally, the true nightmare, gamma radiation. Gamma rays are highly permeating. They pass right through your clothing, your skin, and even standard buildings. The only effective protection here is thick layers of incredibly dense materials, like lead or concrete. Gamma radiation literally permeates the human body right down to the cellular level, causing acute radiation sickness, long-term cancers, and even gene mutations.
Finally, Section 5, the global nuclear arsenal.
Okay, so we've looked at the microscopic science. Now let's zoom all the way out and look at the macro reality of the world we live in today, where 9 different countries currently possess these weapons. I want to directly ask the most common apocalyptic question associated with these stockpiles. Could our current global arsenal actually destroy the entire planet? It's totally a staple of science fiction and pop culture, right? That humanity possesses this self-destruct button that could literally crack the Earth in half. But what does the actual math tell us?
Currently, there are roughly 15,000 nuclear warheads deployed or stockpiled around the world. Now, since they all have varying yields, scientists have to run estimates. If we assume an average yield of 500 kilotons per warhead, and let's say we combine them all into one massive superbomb, the total global arsenal has a combined explosive yield of roughly 7,500 megatons. That is just an unfathomably large number.
But here's the reality check. While 7,500 megatons would cause unprecedented loss of human life and absolute ecological devastation, it is completely dwarfed by natural cosmic events. Let's compare humanity's entire combined arsenal to the Chicxulub asteroid impact. You know, the event that wiped out the dinosaurs. That single asteroid strike was roughly 13,000 times more powerful than every single nuclear weapon on Earth detonating at once. So, to answer the question, no, our current global arsenal could not physically destroy the planet itself. The rock we live on, it would survive just fine. Humanity, however, would not.
Which brings us to a final, really provocative thought. Humanity holds the power of stars in its hands. How do we ensure it remains understood but unused? It is absolutely vital that we understand the detailed science behind these forces. We need to know how implosion triggers fission, how atomic blasts spark thermonuclear fusion, and exactly what kind of invisible threats they leave behind. Because by demystifying the science, we replace abstract fear with concrete knowledge. Let's just hope that by deeply understanding the sheer mechanics of this devastation, we ensure that we never, ever have to witness it in action again. Thank you so much for joining me on this explainer. Keep asking questions and keep learning.